Well, hello everyone. Welcome to today's discussion of Lean, the interactive theorem prover, and its impact on mathematics and AI. This is the second in a series of panels, a two panel series. Yesterday we spoke with several mathematicians, specifically about Lean for mathematics. My name is Kevin Hartnett. I'm here because I recently authored a book called The Proof in the Code. How a Truth Machine, Lean, is Transforming Math and AI. The book came out this week, and we have with us today three distinguished guests who are some of the most important figures in this whole story. We have Leo de Moura, the creator of Lean. We have Jeremy Avigad, a professor of philosophy and mathematics at Carnegie Mellon University, and now the director of a new NSF Institute for Computer-Aided Reasoning in Mathematics. And we have Sebastian Ullrich, the co-developer of Lean 4 with Leo, and the co-founder of the Lean FRO, which today supports the ongoing development of Lean. Sorry, I can't actually see you all, but I thank you for being here. We have the ability to ask questions in the Q&A feature of Zoom. So if you have questions as you hear the participants talking, please post them there, and we have time, we'll get to them. The first question I want to ask is to Leo. So in the proof in the code, I talk a little bit about the history of formal reasoning and theorem proving, aided a lot by a paper that Jeremy wrote, and which was an important source for the book. We go all the way back to even the 13th century and a Majorcan monk named Ramon Lull. We talk about Leibniz several centuries later, and we talk a lot about the 20th century efforts to create formal systems for mathematics and then computer programs that can verify those mathematics. It is a unique pursuit. And so my question to Leo is just what leads someone to want to build this very unique kind of computer program?
Nice, nice. Thank you for the question. Uh, First thing, is beautiful. I think the theory behind is beautiful. There was a lot of excitement at the beginning about learning something new, uh, about building. I think, at least for me, building something is the best way to learn all the details, right? You get a completely different perspective. If you use Lean to formalize math, you probably have experienced something similar. When you formalize something, you get a new level of understanding. I mean, many things that were unclear now become clear just by the act of formalizing something. Same thing is true for when you implement something. You implement it, you get a completely different perspective, right?
Tell me like about well, all right. Let me send the next question to Jeremy, and we talk about when you formalize something, you understand it better. That certainly seems to be have been true in the way people have adopted Lean for math. Jeremy, you had this dream of computer-aided mathematics for a long time, going back to the 90s. You had worked with other interactive theorem provers like Isabelle. You had ideas for introducing automated theorem prover methods into mathematics. Um, Tell me why that is such an appealing vision to you. That's part one.
Yeah, so a lot of it comes from my home discipline, which is logic. I was trained as a mathematical logician. But it even goes back earlier. I mean, as a kid, I was a math kid. I really liked mathematics. But I also, grew up in the early days of computers and, personal computers and all that. And in high school, I read, Gödel, Escher, Bach, which I think turned on a lot of people to kind of formal reasoning. And I see Sebastian smiling. Um, and so, it was like, I was born in 1968, so growing up in the 70s and 80s, it was the time of cognitive science and symbolic reasoning. So I've long just been fascinated at the possibility of um, um, mechanizing, if not really mechanizing mathematics, but having mechanical assistance for mathematical reasoning. The ability to represent mathematics in symbolic terms and describe the rules and get computers to help you reason. So it's just been, I don't know, I just grew up really, really interested in that.
And as a theme in the book very much is that like this vision has been around for a long time, but it never gained traction in mathematics in a very mainstream way for quite a while. Lean, I think it's fair to say, is the first theorem prover that has become a fairly widely adopted mainstream tool in math. There were like a lot of there are a lot of other great ITPs out there who had definite pockets of adoption and enthusiastic users, but Lean, I think, has kind of transcended that in a significant way. And my question is the same one actually I asked our panelists yesterday, but why do you think, and I'm going to ask this first to Jeremy, why do you think Lean is kind of the ITP that kind of broke through in this big way?
Yeah, that's a good question. I mean, I think about that a lot as well. So, I mean, as you say, there are a lot of great proof assistants out there, and they're all, many of them are still active and they're doing great things. So the question of why lean, I don't want it to be construed as a question of why lean is better than any other one and so on. But I think that there were several things that made lean, really good, for the mathematical community. I mean, one is just, I mean, Leo is amazing and just the strength of just the drive for perfection and, the talent and the skill to design a system as good as Lean. As I mean, the real answer to the question is everything in your book, right? So there were design decisions early on, the choice of using dependent type theory, but not shying away from classical reasoning. A lot of it was even almost the early exposition. I worked on a lot of the early documentation, like theorem proving and lean. And when I wrote that, I mean, I've always traveled between different disciplines, but I'm trained as a mathematician. And so, when I would try to write the documentation and explain, how it works, I was explaining it to colleagues and peers, and I've been explaining things to colleagues and peers in mathematics and students for a long time. And so it was really, I think, when people, picked up the documentation and tried to learn the system, it was something familiar to them. But then there were all the other things that were in the book. I mean, there was Mario early on, and just round the clock helping mathematicians learn to use the tools and supporting them in the use. There was Kevin Buzzard and his excitement and just kind of broadcasting and all the the blogs and so on. I mean, there was the enthusiasm from Johan and Patrick and then Heather and Sebastian Guizel and all the people early on. So I don't think I think it was a lot of things that really just came together to make it happen.
Let's talk about some of those early decisions, Leo. I guess maybe a two-parter if you want to take on both of them. Tell me about your decision to base lean on dependent type theory. Like, kind of what were your considerations? In the book, we talk about some reasons that it was not initially your first choice. So why don't you just like tell me about that decision? And then secondly, if there are a couple other key early design decisions that stand out to you that you think kind of made, ultimately set lean on the right course.
Yeah, yeah, yeah. Yeah, I don't like complexity. For sure, dependence type theory adds complexity. At the beginning, I want to go with high order logic. I mean, it's simpler, it's easier to automate. Uh, uh, but one thing that I think was constant is the fact that we listen to the users, right? Some people say, no, Hall is great. All the mathematicians disagree. Most of them disagree, right? You have to listen to your users, right? When the evidence is there that they will not be able to do what they want, you have two options. You give up these users, you say, I'm not going to support them, or you make the change to support them, right? And so listening to your users was a constant, even today. We're going through a massive change because the MathLib maintainers need improved scalability for a specific situation that only happens after 10 years people using Lean. Another aspect decision was not at the very beginning, but it was the points where Lean became popular with the math community, is that Lean is very extensible, right? The math community, MathLib is 2 million plus lines of code, but there are lots and lots of Lean extensions inside of MathLib. Uh, the ability of the math community to make Lean their own was important, right? They wrote automation that's specific, right? Without coordinating with Sebastian and me, right? This ability to make your changes without talking to the developers enables you to scale, right? At the beginning, for many years before the throw, we had very little resources, right? Since this extensibility was super important to scale, right? For people to implement. I think in the book you have a story from Kevin that one day he was trying to prove that 1 + 1 = 2 for the real numbers, and Mario implemented the tactic for him. I mean, the automation for doing that is still there. It's called norm num, right?
Right.
Uh, uh, yeah, this was important. Uh,
I think so. You mentioned kind of at some point you have to decide I'm either going to build for these users or
mm,
give them up. And definitely
yes.
an element of the book is talking about how you came to see mathematicians as important users of
Mm,
Lean.
mm,
So when you first built the program, you were at Microsoft Research. You were thinking about software verification, bug finding, right? Not math. Um, yeah, tell me about the kind of the process you went through to see mathematicians as core Lean users, and kind of when did that
yes.
click for you?
Yeah. I was following at the beginning was super fun. Was Jeremy interaction with Jeremy, with his students. I think we all agree. Sunho was there. Was super fun the first years, right? But around 2017, it starts getting really big. The team. There were many people from the math community did not understand that Lean was a research project, was not a product. They felt like, oh, this is a Microsoft product. I think Jeremy mediated many of these conflicts, right? So in 2017, was lots of tension, and also the feeling like at that times, like people are making unreasonable requests for the project. What's the goal of the project was not clear at that time. A bunch of people for sure were having fun, but I think only in 2020 the goal became clear, right? With the liquid tensor experiments, like you can do cutting edge math with the system, right? And uh, uh, and from there, Sebastian and I at the time were working on Lean 4, and then we released Lean 4 that year. In 2022, everybody was in peace again. I recall this very emotional, was emotional to me. I mean, in 2022 we had events where Jeremy introduced it. I was giving a talk and made the introduction. It was amazing. I mean, maybe Jeremy remembers details.
Of course I
Uh,
remember. I think you can find it on the
yes.
web and you'll
Mm.
see me all tearing
Yeah,
up in the
yeah,
introduction.
yeah, yeah,
Yeah.
What were the
yeah.
tears for, Jeremy?
It was, so with Leo's frustrations, there were a couple of years where he was really holed up and focused on Lean 4, and he really needed some distance from the math community. And that in part meant distance from me. And so, for a couple of years, I had barely, any contact with Leo. And so, and that was hard. In many ways, it felt like, losing a good friend. And so in part, the meeting was getting Leo back, not just to the community, but, somebody that I could interact with. But also, in the introduction, it was nice to express, as a developer, you only hear the complaints from your users, like people saying, I want this, I want that, why doesn't this work? And in the introduction, I tried to express how grateful. I mean, all of us using Lean, we're just having the time of our lives, and we were excited about it, and the feeling that we were in building this library, we were doing something meaningful and important. And so it was nice to be able to convey to Leo that how much we really appreciated everything he had done.
Hmm.
And it's
Yeah.
something I don't think we do it enough. So
Lean 4, kind of the development period of Lean 4 was like an important number of years, both for right, Lean
Yes.
itself, obviously, and for kind of the ultimately I don't know, I think kind of the way in which kind of Leo and the math community come together. And so I want to bring in Sebastian. Tell me what when you demo Lean for the mathematicians at a number of conferences. Tell me your impressions of the community, what they were their goals and their understanding of Lean at that point, and what were you and Leo trying to achieve with Lean for?
Yeah, let's see. So mostly what I demoed at that point, I mean, we were very actively working on Lean 4 at that point. So the demos were of specific improvements that we were working on, had in mind. Often it wasn't actually a running program yet. It was a slide that I showed because in the end it took us years to get to the point where we could release Lean 4. And there was definitely positive feedback there, but also like like Kevin said yesterday in the other panel, I think to many users the point of Lean 4 only became apparent when it was actually there, when they were able to use it, when they were able to play with it, and also just when it allowed Mathlet to grow further than it would have been possible in Lean 3. So yeah,
And
really.
what were the elements of Lean 4 that did that?
We just restructured a lot. I mean, just Leo took, I think, all the experiences from all the prior versions of Lean, and then with a basically blank slate, rethought how does the simplifier need to look? What does it need to look like to really perform in the way that the mathematicians already use it in Lean 3, but where it could become a bottleneck and so on. All these tactics, and yes, I mean that was
So
one.
let me chime in and say it was more than that. I mean, just following up on something that Leo said before, it was the extensibility, not just being
Yeah,
able to write tactics, but also and you were at the heart of you were Mr. Syntax. I mean, you had all these great ideas about how to make the language extensible. And I think we can't I can't emphasize enough how important that was. Mathematicians will go to extreme lengths to get the system to do what they want it to do, right? As long as you give them the opportunity, right? I mean, mathematicians are finicky about syntax, they're finicky about the interactions with the system. They want it to be just right. And Lean 4 gave them the way to do it, to make the system whatever they wanted it to be. And that was you and that was Leo. And I remember in 2020, right before the pandemic, there was this meeting at Carnegie Mellon. Um, uh, um, I guess we called it Lean Together. Your talk, Sebastian, I remember announcing you and saying this is the one talk that everybody really cares about. But just the excitement and the anticipation of of what you guys were doing was really amazing.
This Lean 4. Go ahead.
Yeah. I actually had something with on my but it's already gone. So please go ahead.
If it comes back, yeah, definitely just let us know. I've got actually a couple good questions that people submitted ahead of time that are a little kind of isolated, but I want to ask them because I'm curious about the answers. The first one is to Leo, which is like, why and how did you choose the logical calculus implemented by Lean?
Hmm.
There's that one, and then another one let's throw out to you because we won't get to come back to it, is how do you balance writing a language that is beautiful to computer scientists with the practicality of an ITP that's useful to mathematicians?
Great questions. I mean, again, it's about listening to what the feedback they are giving you. About using dependence type theory, I think we discussed it, right, at the beginning. I wanted a simpler system, right? I mean, that's easier to implement. So I don't like complexity. I love simple things. But dependence type theory is what the community wanted. Another aspect I think you cover in the book. Unfortunately, I had to come to Brazil. My copy arrived at my place, but I haven't read it yet. I mean, but I remember you told me that you mentioned George Gontier. George was working on a project. He was my colleague at Microsoft Research. He was formalizing Faye Thompson using Rock. That's also based on dependence type theory. And he demoed the project to me, and it was quite beautiful, the formalization, how he was encoding everything in dependence type theory. Uh, Basically, it was all the interaction with Jeremy. Jeremy was emphasizes a lot the difference between concrete math and abstract math, being able to have the algebraic hierarchy. I remember one day he told me that if we figure out in Lean how to do it properly, he would run naked. I'm still waiting for him to to do it. I mean, I think he forgot, but now I'm here publicly reminding him.
There's the book talks about a lot about that choice of dependent type theory, and
Yes,
Mint talks about your lunch at Microsoft with Georges Gontier, and also how much Jeremy hoped you would choose that, and the way he kind of celebrates in that moment. Another question that came in from our attendees is for Jeremy, and then we'll move off of type theory. But do you view dependent type theory, Jeremy, as just a clever system for encoding and reasoning about mathematical concepts, or do you see it as a subject with deeper philosophical significance?
So personally, my interest in dependent type theory is really just as a language. I think if you write down the constraints of what you need a language to do to model, algebraic reasoning, um, really the minimal solution, you need X, Y, and Z, and then dependent type theory is the answer. There are a lot of people who study type theory for sorry about that, who study type theory for a living. And so there is a lot of beautiful theory and research behind it. But for me, type theory is more the medium. It's really just the language on which that you can use to express mathematics.
Yeah. I see that Leo is answering a question in the Q&A about, are you sad so much AI in the lean world? And I know you love it. I know you're over the moon that there's
yes, yes,
AI.
yes. I mean, I'm a big fan. People don't. I will tell three phases that happen when we change something. Someone reports a bug. We have to isolate the bug. Then we have to fix it, and then we have to patch libraries and everything. The first and the third steps are horrible, are not fun. Nobody wakes up saying, I want to do this. I remember at the beginning, the first time Jeremy spent 1 month at Microsoft Research, I was debugging, isolating an issue, these gigantic traces. Jeremy arrived asking me oh, it's time for lunch. And he looked at the traces and he told me, how do you do this? I mean, it's horrible.
Yeah.
We did this because that was the only way forward, right? But AI is amazing at isolating issues.
And
Uh,
even beyond isolating, I would say,
yes.
even if you take any already reported issue, already isolated issue in our bug tracker and point an agent at it, it will very likely be able to tell you exactly what went wrong for this bug. I mean, that's of course only one very small part of actually fixing it, but yeah, I'm surprised every time again about
I think
this.
Yes.
the emotional kind of valence of the book would feel a little
Yes.
different if you guys had had AI to
Oh,
debug
yes.
all those years, right? It
Yes.
would have been a little less
Yes.
torturous, maybe.
Yes. And then fixing the libraries also super mechanical, boring, patching things. AI is amazing at that part too.
Hmm.
It's like I compare after you take a hot shower, you can't imagine taking cold shower anymore. AI is like that. I can't imagine going back and working without AI for isolating bugs and patching the libraries and the test suites and so on. I mean,
We're gonna get to kind of a number of AI questions in a minute. I want to ask two before we actually kind of switch to that. One is just another kind of a question that came in from users about the building, or sorry, guests about the building of Lean, to Leo or Sebastian. Did you always have in mind that Lean would have a small, trusted core?
oh
What
yes.
lessons did you learn, or are you learning building this core? And do you think these lessons transfer to the development of other projects within Lean?
No, the trust score was from day one. I mean, yeah.
Yeah, basically, it almost hasn't changed ever since I even came in. So I didn't even see the changes.
That was and a trusted core and keeping it's small so that other people could reproduce it. And that would be kind of the form of assurance, the way of gaining assurance that it was correct, right?
Hmm.
Yeah,
Yeah,
yeah.
yeah.
From the very beginning. I mean, Leo was that was, in fact, he even did things that, I remember at the time people thought were crazy, to get more complicated forms of recursion. Other systems would just kind of build them in, but Leo would compile them down to these very basic, very simple primitives. It was a tremendous amount of work, but Leo, again, he would not compromise on that.
Mm.
Um, All right, so kind of a transition question here, and this is like something I've been trying to like kind of get my head around. The book is the arc of it, the narrative arc is kind of triumphant. It's this kind of long shot
Mhm.
thing, this ragtag band of people, and by the end of the book, we're feeling like that lean is going to be here to stay. It's like change the way math is done. There's no worry that the program is going to ultimately disappear for lack of support. So it's a triumphant story. But then in the last year, AI just completely changes the trajectory of AI, of lean. It's just like so much more essential in so many different ways. So it's almost like you you planned for one scenario and then a whole new scenario has happened. I guess what I want to ask is a question I asked yesterday, this counterfactual. Like, how did you feel a year or two ago, before AI really changed the applications of lean, about its kind of place in the world, its importance, its like the likelihood that people lean would be around in 20 years? What did you see the path lean was on in a way pre-AI? And I'll just open that up to anyone who has the thought.
Well, I, we always felt, I mean, uh, Sebastian and I co-founded the Lean Flow, but Jeremy is in the board of directors from day one. I mean, we have been together discussing the path before AI, and we felt like for math education was clear we would be able to do huge impacts. For math, even without AI, we saw the potential of people working together better. This was clear to us also. We saw this path. Uh, but for software verification, for us would be the same safety critical systems because it's so expensive. So for safety critical systems, we're going to use Lean. We felt like we have a good shot there. We're going to be successful there. But these were all niche, right? We didn't expect Lean had the potential to become mainstream in math or software verification. It would be a niche tool. Some people would adopt it, others would not. But now with AI, it changes everything. Now it can be mainstream for software, for math. It enables. I see people may have restrictions. I understand the restrictions they have about AI, but it is enables people, accelerates people. Yeah, it's yeah,
So,
it changes. I think the impacts now can be much bigger.
so in your
Yeah.
mind, lean was, go ahead, Jeremy.
Well, I'll just chime in and say, so from the beginning, Leo always characterized the four pillars or target audiences of the Lean FRO were mathematics, computer science, education for both mathematics or computer science and AI. And in the early days of trying to understand, which to attend to, which to focus on, initially AI was the more risky one. It's like, well, we don't know how that's going to play out, but certainly mathematics, certainly software verification, certainly for education. So I think, what's changed, if anything, is realizing that okay, AI, it is the AI lean interaction really is going to be successful. But as Leo says, I think it really most successful in amplifying the strength in the other domains in mathematical reasoning and in software verification and so on. It just makes Lean an even more powerful tool and more capable of going into the mainstream.
I'm going to ask a bunch of questions about math in a second, but actually, I did not get to yesterday lean in education, and you brought that up, Leo, and you just mentioned Jeremy. What is the vision there for ways in which lean is a powerful educational tool?
Go ahead, Leo.
No, no, go ahead, go ahead, go ahead. I just answered the last
I
one,
bet
Jeremy.
we're still trying to figure it out. I think there are pros and cons to using, proof assistant. Let me even just focus on teaching mathematics. Um, um, on the positive side, on the negative side, students are learning this funny syntax. It's kind of a, sometimes in some ways it can be a distraction from the mathematical ideas if you're focusing on the system instead of the mathematics. But the most powerful thing is that you're getting this immediate feedback, immediate interaction. So somebody, sitting down and using a proof assistant to explore mathematics, you get the signal back as to whether you're right, whether you're wrong, and when you are making progress, not only do you know it, but you feel it. There's this visceral feeling of success. And so the ability to kind of draw in students and engage them, as long as it's engaging them in the right way. I mean, we're still trying to figure out how to use the tools effectively. But I think that kind of the immediacy and the engagement is really, really very powerful.
Yeah, I agree with Jeremy. But Jeremy, I feel like if you're a nerd, it's great. I mean, I would love to have something like Lean when I was a student. And
Yeah.
I
What drew me, sorry, what also drew me directly to mechanized mathematics was just this, and maybe this is from a more computer science standpoint, to have this ability to say, oh, but what exactly is the definition of this? And then you see, oh, it's defined in terms of these three things. But what is the definition of that? You don't want to ask that in the middle of a university lecture. That would be distracting. But if you're sitting at home in front of your lean session, you can just click through everything and explore that. It's such a strong teacher, and it's also, yeah, to me it's fascinating.
in the book I mentioned that teaching is one reason a lot of the early people came to Lean. Kevin Buzzard wanted to use it in his Intro to Proof class, and he said that he would have students submit homework and then he would have to mark it a zero because they literally proved not one thing. And they would say, I have a full piece of paper, but they proved not one thing. And the feedback cycle is so long on that, right? If
Yeah.
you get your homework back a week later with Lean, you can get that immediately. But the book also talks about how it was a disaster when he tried to use it in 2017, 2018 in his proof class because kids didn't really understand mathematical proofs and they didn't understand this lean language they needed to use to. So it was just like a kind of doubly complex. My question is with LLMs that can write code now, does that make is the barrier to entry to lean for like undergraduates, is it lower, or do you still need to be engaging with the syntax to really be getting the learning benefits?
yeah, I think the barrier is lower for sure. But there is a danger, right? I mean, I view AI, if you're excited about the subject, it can accelerate you a lot. If you really want to learn, it can accelerate you a lot. But if you do not, it can be used to do all the homework so you don't learn anything, right? So that is two extremes. If the student is not excited about the subject, and I took many classes where I was not excited about the class, but I learned it because I was forced to. But with AI, you can use AI to do all the homework, everything. Uh, yeah,
Yeah.
Yeah, I was going to say almost exactly what Leo just said. I mean, there is a lot of ambivalence about AI in mathematics. And on the positive side, it can be a help and a way to explore and a way to learn that kind of amplifies, your ability to explore mathematics. But there's a danger that it'll also kind of replace or discourage these critical thinking skills and this kind of deep thought and engagement that mathematics really needs. And so, there are pros and there are cons, and we just have to be careful.
Let me ask a math and a lean question. Okay. So the book has a chapter on Google DeepMind's development of alpha proof, which they use to win the or get a silver medal level score at the 2024 IMO. They're using lean as the RL reinforcement learning environment for alpha proof, and then also the way to kind of check its final outputs when it takes the IMO. I know today, I think a number of startups are using Lean really as like the way to train their own agents or models. I think Harmonic is using Lean quite intensively. I know Axiom talks about using Lean quite
Mhm.
intensively. There's also this recent OpenAI proof, the unit distance conjecture, where my understanding is it was not using Lean. I think they did it right. It was just an LLM that outputted a proof, and maybe experts looked at it.
We don't know how it was
We
trained,
don't know. We
so
don't
it may have
know.
been right,
That's
but at least on the surface, in the result, there was no lean had no
right.
place.
So I guess, yes, that's right. So my question, how should people think about lean's place in kind of research mathematics at this point in time, where in my mind there's this RL stuff that's going on, but then there's like a separate kind of maybe a separate thing, like we saw with the OpenAI proof.
So can I try my hand at this one? Yeah, so there is the last few years there's been an explosion of interest in AI for mathematics and getting AI systems to do mathematical reasoning and write mathematical proofs. And as you point out, there's both getting it to write informal proofs and getting it to write formal proofs, or taking informal proofs and formalizing. And I think the jury is still out. People still go back and forth about the role of the formal, the role of the informal. But I do think that most people working in the area believe that it's really the combination of the informal and the formal that's really powerful. I mean, mathematicians really prefer, I mean, to reason informally and just read ordinary prose. It's no fun reading a formal proof, reading formal code. Um, uh, but um, but on the other hand, the formality gives you the strong signal for correctness. It gives you this precision. It gives you this very crisp reference source, a library that you can refer to, and the meaning is entirely unambiguous. So I think the most promising directions around AI for mathematics use informal tools and reasoning where that's appropriate, using formal where that's appropriate, and get the two to interact. It's really using them both and getting them to interact well.
Okay, let's see here. The I know Axiom, the startup Axiom, talks a lot about um, training a model using Lean to do math. But what they very much advertise the benefit of that, or they very much emphasize the element of software verification. That somehow some type of model that is very good at doing math is also being good at kind of verifying AI outputted code. To Leo and Sebastian, how do you see well, in the first place, what do you see as the application of Lean for verifying AI outputted code? And do you see kind of success there is related in any way to success training math models?
Yeah, for sure. I mean, many disciplines of computer science to verify code, you need a lots of math, right? Cryptography is one of them. Differential privacy is another one. There are many others. I mean, the cool thing about mathematics is that we have MathLib, right? I mean, you're not starting from a blank slate. And the math community has good abstractions also. The proofs in software verification, they have a different, they're much bigger, but they are shallow, right? There are usually no deep insight. When there's a deep insight, it's coming from the math library, the deep insight. Uh, for software verification, the main challenge is scalability, right? AI is really good. We have already evidence that AI is really good at both proving math results and verifying software using Lean. But one thing that's we are working really hard at the Flow is at the scalability of Lean itself to make sure that we will not run out of steam. It's not the AI is failing. Lean is not scaling to big software verification projects.
Hmm. In what way, and if you have thoughts here, Sebastian, in what way is Lean not scaling right now, and to what kinds of projects?
I think it's more that people are just always more ambitious than we expect to, and they are just coming with the next big project to us, doing something special in that project that wasn't done before, and then we have to think about that again. Oh, how can we actually make this one fast? Yeah, and well, and then of course there's Mavlib that's just growing and growing, and then we can see that, oh, something that 2 years ago we knew was a bit slow but not really a bottleneck, now we see, oh man, we have to do something about this. And yeah, I think that's mostly how it works.
Hmm. You, you,
I'd like to mention that I think there are applications of AI and Lean to areas that are beyond just pure mathematics and computer science. I mean, especially in engineering and all the places, and applied mathematics, all the places mathematics is used in statistical modeling and modeling complex systems and designing chemical experiments and medical experiments and so on. These are all components where you have these mathematical models and you have to reason about them and understand them and explore them and make sure that your reasoning is correct and implement them computationally. And so I think yeah, I think there are lots of opportunities for different types of reasoning. And some of them will be kind of, I mean, Leo describes that, computer science, the proofs are shallow, but it's just the complexity of the system. In mathematics, proofs can often be shorter, but they're just kind of deeper and so on. But I think there are, engineering applications where the systems are both complex, but involve, mathematical reasoning about cyber physical systems, control systems for, things evolving over time. Um, I think the next few years are going to be really interesting as people figure out how to really, put the tools to use and make systems more reliable.
Yeah, I want to ask kind of what should people kind of be picturing? I mean, I work my day job is for the AI coding platform Cursor. Obviously, AIs can output code quite easily right now, and a lot of the big challenges are figuring out how to kind of make that code good and have confidence in it, and like, so you can just kind of go ahead and merge it. What should people be kind of thinking about Lean's role in that kind of life cycle at this point? Could we expect that like almost all LLM generated code gets a specification and like a formal element? Could things ever be like that fast? What would you imagine kind of in a mature state Lean's place is in the software development life cycle?
Yeah, I think it would be really cool if in the future we are focusing way more on specifications, right? And let the AI to write the code. Another possibility, I mean, people say, oh, I don't know how to write a specification. But we usually know, all of us know how to write an efficient version of a program. So the amount of effort that is spent in the industry optimizing code, right? If you have an AI that can prove that the optimized version is functionally equivalent to your inefficient version, this is already super valuable, right? Another scenario that people spend lots of time in industry writing the same thing over and over again, but optimizing for different hardware is a way, I view it as a waste of human talents. Nobody has fun doing that, right? I mean, letting AI to do it, I think would be a huge win. But for me, the most exciting part is being able to work in a much higher level of abstraction.
Say more about that and kind of in what ways are you seeing that in your own work, maybe your own development of Lean right now?
Right now, the AI is not good enough to help us a lot. I mean, it can suggest good optimizations. We made some experiments where the AI helped us to optimize different parts of Lean. This was good. But right now, for me, we're getting lots of value for isolating bugs, patching the libraries. For new territory, like, I mean, you write the spec for something you want to implement in Lean and expecting the AI to get a super clever implementation. This is not happening yet at this point. But I think probably it's just a matter of time.
I'm going to do a quick housekeeping question, or not any small question from the chat here. Is there a best LLM at writing lean code that people should be using?
Yes. Right now, well, it keeps changing, right? I mean, but right now, I don't. Can we say
Why
publicly
not?
these
I
things?
think
Yeah,
it's
I think both Claudes and Codex are really good. I mean, we get the link row is split. I mean, there is half of the link row. Oh, not half. I think 80% of the link row likes Claudes and 20% Codex right now. I mean,
okay.
and it keeps changing. They keep getting one gets better than the other one.
But you feel like
But
people can
I'd like to come back to the
specifically,
previous question though and add something. I'm sorry, go
yeah.
ahead, Sebastian.
yeah, just wanted to say this is about programming in Lean.
Yeah.
Um,
Yes.
Yeah, specifically about that. Go ahead, Jeremy.
Yeah, so I mean, on this notion of the workflow with using AI and Lean with verification, I think one reason that Lean tools like Lean are so important in the age of AI is that they are a medium for the interaction with the user, right? So Leo describes a situation where we just write the specification, right, and then AI writes the code and proves correctness and so on. But even writing a specification is hard. Like often we don't know exactly, but now having a tool where you can sort of write a specification, then AI comes back and gives you something formal and you look at it. But maybe AI says, well, is this what you want? Here's a test, maybe here's a counterexample. It's being able to go back and forth. And you ask AI a question, you get an answer, but the answer isn't a formal artifact. It's something in front of you that you can look at and query and probe. And then you ask questions. It's the back and forth that's going to keep us in the loop in the interactions with AI and making sure that
Yeah.
we're getting what we want and that we have reliability. It's not having the proofs of correctness. It's understanding what we're proving and what we're stating and what we're
Yes.
reasoning about. And I
Yes.
think that's really the power of like an interactive system like Lean.
Um, I want jump is jumping a little bit, but a question that I didn't get answered, I didn't get to ask yesterday, but was about MathLib's role in all of this. I think in the kind of the years covered in the book, there's just a clear understanding of what this MathLib's growth enables kind of more formal mathematics. It just like lowers the amount of work you have to do when a new result comes along. There's just a lot of talk about building up MathLib from the ground up. AI has definitely like scrambled the picture or changed the picture in different ways. Um, what is the role of MathLib today? Is it changed with AI and LLMs? And kind of what do you think, what is the role of MathLib for math research, for software verification, and kind of what should we, how do you hope to see it develop?
Let me jump in first, then maybe Leo and Sebastian can correct me or disagree. But I think the fundamental role of MathLib does not change. Having a carefully curated, well understood, well designed library that the community comes around and works together to develop and understands as just kind of a solid platform on which you can build all kinds of things. I think that's what the maintainers have long been doing, and I think that's what they're still after. And I don't think AI changes that. I think AI
Yeah.
makes it easier to build things on top of MathLib, to go explore, to learn. But at the end of the day, you really want a carefully designed, thought out library that we understand and can use and build on.
Yeah, I fully agree. And AI is helping us to maintain MathLib right
Yeah.
today. I mean,
Let me ask, someone mentioned this in the Q&A about CSLib, which is kind of an analog to MathLib and maybe more relevant directly in software verification context. Leo, Sebastian, tell me kind of your views on CSLib and its like role ultimately, or not, I don't know, in software verification.
yeah, I'm in the steering committee. I have a minor role there, but I'm a big fan of CSLib. There are two pillars in CSLib. Theoretical computer science. Basically, it's this one is very similar to MathLib, but for computer science. We want results that people teach in computer science courses covered in CSLib. And the other pillar is software verification to have infrastructure that makes it easier for people to verify software using Lean. Of course, CSLib is much younger, right? So I think it's around 100,000, maybe more now. But the last time I checked, it was already above 100,000. But yeah, I think it will be a key component of the Lean community in the future.
How does like a mature CSLib, Sebastian, aid software verification, and kind of how would you describe the current state of it?
Yeah, I think that's a really interesting question, especially in comparison to MATLib, because I think there will be definitely parts in how CSLib will work that will not be like MATLib, and some that will be. A lot of this is just, I guess, foundational because computer science is just much younger than mathematics to begin with. So I guess it's not as consistent, maybe, as curated yet as mathematics, which will perhaps happen in the future. Maybe CSLib can play a role in that. But yeah, ultimately, um, I find it actually hard to see how exactly projects built on top of CSLib will interact with it compared to MathLib. But yeah, I definitely see people coming together, figuring out what's the common objects between our projects, what should be in this library, and yeah, I think that process is starting now.
Let me jump in and mention that there's been a launch of PhysLib, a library for physics. There's been talk of developing a StatLib, a library for statistical research and statistical applications. So, and they're all exploratory. We're all still trying to figure it out.
I want to ask an off-the-wall question that came up at a recent event for the book. I was talking with a couple of mathematicians, and we got around to the idea, this is going to be out of left field here, using an LLM in kind of alpha zero style to rebuild mathematics in the ground up. You just give it the basic rules, you give it lean as your RL environment, and you see what it comes up with. And the question was, would you expect that to, how far could it get? And would you expect it to look like our human mathematics? That's the question I want to pose, I guess, to Jeremy, but I'm curious if Leo or Sebastian, you have ideas as well.
Yeah. I don't know if I have any insightful answer. I mean, for me, mathematics is such a fundamental human activity. I don't really care. Tell me that there's some AI off there developing a new mathematics from the ground. Maybe experimentally, just to see what happens, would be kind of interesting and fun. But what I really care about is how it helps us do mathematics.
Hmm.
So, and
Is
that,
math solvable? This I never even considered this idea until I was on a podcast a week ago, and the Hard Fork podcast, and they asked something about math. Would we ultimately get to a solved place? And I was thinking, I don't think it's that type of discipline.
Well, it's about what you mean by solve. I mean, so we know algorithmically there's no way to decide the truth of any question. And actually, when people are critical of your title, it's not a truth machine in that it'll decide one way or the other. It's a truth that helps you, a machine that helps you establish truth. But still, the process of deciding which truths are important, which truths we should care about, why. I mean, it's easy to generate lots and lots of truths. Figuring out which ones we should care about and why and what we should do with them, that's the human part of the story. And I think that's AI is not going to take that away.
Which is very much a point in the Leiden Declaration that you were one of the early signers of, which has kind of come out recently. Leo is typing. Good. How can we help with the development of lean? Um, yeah, I was curious about this question that came in about 20 minutes ago. Leo, is there anything in lean's design that you would change if you were to build it from scratch today? And specifically, is there anything that would make it more amenable to like the way it's being used now?
Yeah, it's a good question. I mean, we're very happy with the design. Uh, uh, People keep asking us if there's we will have a Lean 5. The answer is no. We are going to keep improving Lean, but there will be no discontinuity, right? I mean, it starts with a new system that people have to port everything. Uh, uh, we are happy. Of course, we are going to keep optimizing. We know there are many places that we need to improve. Like Sebastian said, no matter what we do, people will always try harder problems. So scalability will keep going. I mean, forever, I think. And now, maybe at one point, AI will be doing that for us. I mean, but I think you ask Jeremy about math, if AI could build a math lib from scratch. I
Mhm.
agree with him, it's not there. Same thing for building a system as complex as Lean. It's not even close. I mean, but it's extremely useful. I mean,
Mhm. With the remaining minutes, I'll kind of throw it to each of you. I'm just curious what you are working on today, in this realm, and what are kind of the questions or open challenges that have you most excited? And maybe we'll go down the line. We'll go Sebastian, Jeremy, Leo.
Hmm. Well, that's a great question. Let me see.
scalability,
Uh,
Sebastian, come on.
yeah,
Yo,
yeah. So, I mean, I was thinking of how to, what's the exciting part of that. But yeah, I actually, one of the most exciting parts I see when working on Lean is just people using it in more and more exciting projects. If they are doing something exciting that maybe 2 years ago wouldn't have been possible in Lean because it wouldn't have scaled, then that's the most exciting part for me. Just making things faster. This is the ultimate drug for me.
That's a very user's first answer. Yeah, Jeremy, what are you
Yeah,
excited
so
about? What's on
for
your
me, from
mind?
the beginning of the project, I mean, the interest was in figuring out how to make formal methods and lean useful to the mathematics community. I mean, I've loved mathematics. It's my home discipline. You want to feel like you're contributing, doing something useful. And so And so now, with students, we're still working on ways to understand how to use Lean and AI to do things that are useful for the mathematics community. And as director of the new NSF Institute, again, our mission is to try to support the math community in these crazy times. I mean, these times are crazy, but trying to figure out how to use the technology and how to use it well to support mathematics.
And do you have any particular kind of, promising ideas there or kind of, initiatives you're trying to drive?
So a lot, again, I think the success of Lean was realizing that the way to have an impact on mathematics is not to figure out how yourself, but to get the tools in the hands of mathematicians, make sure they understand what they can do with it, and let them figure it out. So it's really more kind of a supporting role, trying to help the mathematics community figure out what they can do with the tools and what they want to make of them.
And then with our last minute, Leo, tell us what you're thinking these days.
Scalability. I mean, I'm currently we call at the Lean Flow we call it a factoring nightmare. Is we are making a change to improve scalability in Mathlib. But I'm also working a lot on scalability for software verification. And another thing we have to do next quarter, after we are done with the refactoring nightmare, we are going to have to optimize the type class resolution. Type class is a main feature that's massively used in Mathlib, and we need to improve now to make it scale better. Will be the
Kevin
next
likes that.
nightmare. Yeah,
You just got a heart from Kevin
he's
Hartnett.
complaining. Yeah, he keeps complaining. He's the one.
And Leo and I even have orthogonal ideas for that. That's the best part.
Yes.
Good work to do. I think that is a good note to end the conversation on. Leo, Jeremy, Sebastian, thank you so much for joining. It's
Thank you.
Kevin,
got to
thank
talk.
you so much for everything you've done.
Oh,
Yes.
absolutely. It's been a
Thank you.
pleasure. I love writing the book. I love seeing you all routinely for a while. I say in the book I was sad when the book was over. It meant we didn't get to see each other every week. But great to have this hour to get back together. Thank you all for joining out there. We're all, available in various ways on Twitter and such places. Please reach out. I hope if you're interested in the book, you will consider purchasing it. And we'll have to convene again. So anyway, thank you guys.
Thank
Bye.
you, Kevin. Bye.
Bye-bye.